All right, what's up, guys? Chris and Ninja here. Let me just make sure that I can hear myself. Oh, yeah, we're good. We're good. Okay, yeah, so welcome back to Study Sessions. I'm your host, Chris the Ninja, and today we're going over op amps. Just gonna move this over here. Hopefully, y'all can still see this. Let me re-share the screen. Yeah, yeah. Okay. Yeah. I just want to make sure that y'all see this. What the why is this taking so dang long to Okay, let me change the view. You oh snap. That's a bright light. Okay. So welcome back to Study Sessions. I'm your host, Chris the Ninja, and today we're going over op amps and their types of circuits. So shoot, I should have opened OneNote first. Um, just a quick overview of operational amplifiers or op amps as they're so called. So let me find my mouse real quick. Come here. Okay, and then OneNote. This is kind of crazy because I'm like dual monitor. Like I have both my screens up. Oh my, what the cheese and what is this? What is this? Golly, I can't freaking see this. It's too freaking no, I can't. It's too bright. Ah, gosh, bro. I um golly, man. Hold up. Uh, what is this stuff? The freak. Okay, we're just gonna go back to what? Okay, this is this one. This is this one. Is it in my other drive? Golly, man. Thank goodness I was able to pull this stuff out. Switch the thing. Um um no, that's not where it is. Hold up, y'all. I'm sorry. Okay, cool. That this helps a little bit. This is just because like I can't like I'm very bad at seeing stuff when it's like light on like contrast. I'm telling you, the contrast freaking kills me every single time. Let me see if I embarrass myself at all, like trying to have people, you know. Oh, great, awesome. No one's in here yet. I don't think. I think that's just me. This is just because contrast. Yeah, cool. It's just me. Okay, so now that I've successfully made a fool of myself for like the first 5 minutes of the thing, um, let's get to work. So op amps. I think I'm sharing this screen. Okay, yeah. So op amps or operational amplifiers. Operational amplifiers are a very useful device. They're used most commonly in AC signals because they can amplify the signal that's being put through them. Um, so you can go from let me just write this as I speak because this is it's important. Um, so op amps are pretty important because first intros. Here's how you draw an op amp. Here's how you draw one. So, oh, goodness gracious, my art skills. So you have a plus and a minus. A lot of times they're drawn upside down because what tends to happen is we use op amps with a negative loop gain, but they have two terminals, input to positive and negative, and they have an output here. Um, so essentially, you're trying to get a large gain. So you have a gain that might be denoted as AO or GO. Sometimes it varies depending on like your on who's asking you for what. But essentially the gain is how much comes out over how much goes in. An easy way to do that. So for open loop gain, so we'll say open loop. I'm going to zoom in right there so I can like kind of write a little bit more carefully. Open loop gain, ideally, is infinite. But if y'all saw that video I made, infinite gets beat every single time, even by zero. So there's no real situation where we have an ideal gain of that infinite loop. So really, in reality, you might get a gain of like 1 million or something like that. Might be 100,000, might be a gain of 20. Depends on the op amp. There's multiple different hundreds and hundreds and hundreds of different types of op amps out there. And all of them have a different gain and open loop gain. And um, that all also goes into the slew rate. So you have a slew rate. The slew rate is how fast an op amp raises to the output of the input signal. Now that may not make much sense, so that's why I'm going to draw it out because I'm a very visual learner. I'm very hands on. So here's how you can visualize that. What do you mean? How fast an op amp gets the gain? Blah 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 as it raises to the output of. I'll show you. So assume we have like this box I'm drawing here is like is an XY plane, and we have some signal going like that, right? So we have that signal coming through the plane. We'll call it a sine wave. It's actually pretty close to being a perfect sine wave, but as we know, nothing is perfect in this world. And since nothing is perfect in this world, this is a great example of what I'm trying to show you. So this signal goes into our nice, lovely op amp. So this is connected here and here. Actually, no, scratch that. This is connected here, and then we'll just say this is connected to ground. Now, the important thing, the resistors are not important right now. We'll get to that in a moment. But what I'm trying to show y'all is that the open loop gain, when you put this to a probe, so we'll just say like this is our probe. This probe, if it's measuring how quickly it rises up to that output, so let's just say it's like a gain of 10. open loop gain of 10. So like let's just assume that this is 10 times larger. So this slew rate shows you when it peaks, um, it'll take a slight moment to get to the top, and then it'll take a slight moment to get to the bottom, and then it'll take a slight moment to get to the top, and then it'll take a slight moment to get to the bottom. So it looks very similar to the other signal, but it might have like, let's just call this point -0.5 milliseconds. Might have like a half of a millisecond slew rate, and that shows you how fast the signal can change from positive to negative when it's going through the output. I probably explained that horribly, but just look up slew rate in your free time, and you'll understand it a lot better than what I could probably explain it as. We're going to live stream until I run out of Gatorade. We're not, well, either we're going to live stream until I run out of Gatorade, or until I finish the homework. Whichever comes first. So I'm gonna go ahead and check the stream real quick, make sure that no one's tuned in, asking questions, anything like that. Great, awesome. Um, wow, I gained 6 subscribers. From what? What did I gain 6 subscribers from? What? Dang. Hold up. Let me. Golly, 6 subs. That's crazy. That's crazy. Okay. Um, yeah, so I went to bed last night and I gained 6 subscribers. Oh my goodness. Over the night. But that's not the point. That's not the main point. Also, I got me some snacks. Hashtag not sponsored, but these things, they smack. Uh, these just hit different, man. I'm telling you, these fruit snacks, they hit different. So little snack break. Oh, geez. Hmm, hmm. Okay. So now that we know what the slew rate is, we can talk about closed loop gain. The closed loop gain depends on whether you're working with an inverting or a non-inverting circuit. Now, you might be asking, Chris the Ninja, the freak are you talking about? What is a non-inverting versus an inverting circuit for an op amp? Like, I don't even know what an op amp is. I just told you what an op amp is. Rewind the stream, go back, learn what an op amp is. Now, to answer your question about the closed loop gain, closed loop gain has two possibilities. Um, you can either have negative gain, and that comes from an inverting op amp, or you can have positive gain. That comes from a non-inverting op amp. Man, these fruit snacks, like these things smack. Not small Welch's. If you see the video, holla at your boy, Chris the Ninja on YouTube, drop a little sponsorship deal, made with real fruit, tasty. Hey, I ain't ashamed. And Gatorade, PepsiCo, if y'all looking to sponsor a small time YouTuber, hit me up. The numbers won't lie to you now. Anyway, negative gain. So how will we draw an inverting op amp? Well, an inverting op amp is drawn like this. And I'm going to draw the op amp upside down because it's easier to show it it's easier for me to draw it this way. That's how I learned it. So you have your negative terminal here, positive terminal here. Your positive input is grounded, has some resistor here. Your negative input has an input resistor, and it's connected to some power source. It has to be an alternating power source, like an AC current, AC power source. Then you ground that. This might be, let's just say 5 volts. All right, 5 volts. So RI, this is RI. We'll say this is 5K, 5 kilo ohms. And then this is looped back. Oh, geez. This is looped back with the feedback resistor, RF, at let's say 25K, 25 kilo ohms. Now, your gain for this circuit would be a gain of -5. Now, you might be like, Kristen, how do you just do this stuff in your mind? Well, it's simple. For an inverting op amp, the gain equation, I'm not doing the derivation because I didn't have to learn the derivation. Well, I think I did learn the derivation. I just don't feel like doing it. There's a transfer function. You can look all this stuff up in your free time. I'm going to just get it to you straight. The gain equation is negative RF over RI. Now, if you have now we know our RF value, 25,000. Our RI value is 5,000. That breaks down to just 5. But since it's a negative, it's inverting. You see it's going into the negative terminal. You have to remember that negative number because it's a gain of -5. So if it's gain of 5, put 5 volts in. If you were to put a voltage meter here, you put a voltage meter here, that reads 25 volts. Pretty easy, right? So then, if you want to find the gain in decibels, so in dB, you're going to do 20 log of V out over Vn. Now, I truly cannot remember how to do this backwards, but I can do it forward. Where's my calculator? Hold up, y'all. I lost my calculator. So, using our handy dandy TI-84, hashtag not sponsored, we're going to take 20 log of V out over Vn. Let me check the chat for questions because I'm high key of not looking at any of these questions. Let's see. TI-84, hashtag not sponsored. Okay, cool. So we do 20 times logarithm of 25 volts over 5 volts. Oh. Man, now I get it. Now I get how to get that. Man, that's crazy. I think I know how to get that. Do I understand it? I don't know. Maybe I get it. But 20 log times that, divided by that, that gives us in decibels. Oh, geez, thing's upside down. In decibels, this has a gain of 13.97 dB. And this is negative. So it's really like 1 over 13.97 times 10, or 10 to the 13.97. Something like that. I think that's how decibels work. But that's a non-inverting op amp. Now this is the inverting op amp. A non-inverting op amp is very similar, except the equation is slightly different. So when you're drawing a non-inverting op amp, you draw it this way. Excuse me, y'all. So this is how you draw a non-inverting op amp. Now the difference here is that you're powering the positive terminal, but your loop still goes back through the negative terminal. Your feedback still has to go back through the negative terminal. This is a very important concept that you should learn now before you get to college and someone asks you, draw a non-inverting op amp, and then you draw it wrong, and then you get embarrassed in front of the classroom like I did. Don't get embarrassed in front of the classroom like I did. Be better than me. Don't be sorry. Be better. So same thing, except now our equation goes from negative RF over RI to 1 plus RF over RI. That makes a big difference because now if you try to get too close to 1, your gain is too low. You can't get a good enough gain, and it distorts the signal too much to where you can't see it. So you'd have to do you honestly have to do like an inverter into an inverting into another inverting circuit, but that's stuff that we'll get to in a little bit. Um, so let's see. This is solved basically the same way, so I'm not gonna bother going through the redo. Only difference is that you have 1 plus 5, and that gives you 6. So it's a gain of 6. So this gives you more gain, but it comes with some drawbacks as well. So there's some times where you would need to use this, and there's times where you wouldn't need to use this. It really depends on the application. Um, but yeah, now that we know what an op amp is, there are a couple different ways you can use an op amp. And an op amp can be used to detect different voltages um, because it essentially what it does is it tries to force both of the positive and negative terminals to be the same value. And at that same value, it's dumping a literal mountain's worth of current back into the feedback. It's dumping so much current. If it wasn't on a small scale device, it probably would kill you. Like, this is why you can take things like 5 millivolts and turn it into 50 volts, or 5 microvolts and turn it into 5 volts. That's what this thing does. It forces so much current back through to give you a big, nice, readable value. But you might be asking yourself, well, the freak happens when I have 50 volts and I have a gain of 50 or something like that. Well, there's I forget what it's called, but today we're going to call it the signal cutoff. So the signal cutoff graph. So let's just call this like 0 hertz, and we'll say this is like 10 megahertz, just for illustrative purposes. And then this is like 0 gain and like 10,000 gain. We'll say 10K gain. So at 0 hertz, at a DC signal, you might get 10,000 gain, but there's no like change. And as you approach a higher and higher signal, your gain gets lower and lower. Now, when you think about it, it makes a lot of sense because if you're trying to dump so much current, it takes nothing in this world happens instantaneously. Even the sound of my voice takes some time to travel through the microphone into the audio receiver of the computer to then be rectified and polished and then turn into some probably ugly sounding audio to y'all because I'm using a webcam microphone. So the faster your signal is, or the higher your frequency is, the less time your operational amplifier has to amplify the signal. So we'll say this is like maybe 2,000 hertz here. I might only be getting a gain of 40. This is not the scale, but like this is just for reference points. So this is like I think this is the band cutoff frequency or bandwidth cutoff. Something like that. It's a spec you'll specification you'll find on a spec sheet or on a data sheet for an op amp. I just can't remember exactly what it's called right now, but this is something that happens in the real world. Why did I say that? Why did I say this part right here? Um, frequency cutoff. Oh, that's why I said this. So knowing there's a certain cutoff to different gains, so you don't always have infinite gain. Some op amps have rails on them. That's to say, some op amps are drawn like, or some op amps are created like this. So some op amps are created like this. Now, this kind of op amp is a way you can detect voltages, or you can detect where something crosses zero. Because if you put just a little tiny piece of current or a little tiny bit of voltage, but a little like a very small voltage here, once it crosses a certain threshold, that gain is going to go up to this maximum VCC value right here. So the gain might be, let's just say, gain equals 5. If this here is 7 volts, well, no, let's just do 10 volts. If this here is 10 volts and this here is minus 10 volts, well, in that instance, once, goodness gracious, that's an ugly arrow. Once this voltage here surpasses the minimum voltage needed to get to 10 volts after gain of 5. So let's see. So 2 volts. After 2 volts comes in here, this is saturated. This is completely saturated. So if I have a 2 volt peak to peak signal, well, let's say we have a 5 volt peak to peak signal. So 5 volt peak to peak signal. If I have that coming in right here, After it reaches 2 volts, which is like right about here, this the op amp's output looks like this. Now, oh, hold up, y'all can't see it. Output looks like that. That's a square wave. We put in a sine wave. The freak is that? What? I'll tell you what it is. This square wave is detecting where it crosses a certain point, and you can make this a comparator. This is like the essentials of a comparator circuit. So now that we know all the basics that I think y'all need to know about op amps, at least I hope y'all know the basics enough what I need y'all to know about op amps. We're gonna switch gears. Gonna come right here to the homework problems. So complete the schematic for a non-inverted zero crossing detector. Oh, I need to look in data sheet for this. So here's something that will help you guys, future engineers and smarty pantses of the future. If you have something that looks like this that you don't know what the cheese you're looking at, look up the data sheet. So we're just going to use an LM741, I think. And we're going to look at the pinout for this. We'll take a little snack break. Stuff good. Very busting. Mm. Man, they're so good. Okay, yeah. So as you can see here, um, you can see that where the inputs are and stuff like that. So if we go back here, asking us to create a non-inverting. So non-inverting. First thing we need to do is make sure the power supply gets connected to the positive terminal. Over ice, I'm freezing. So power supply gets connected to the positive terminal. I think that should show up. This gets grounded. It should pop up eventually, I think. I hope it does. Um, matter. Okay. Let's go into here. Can I refresh this? Okay, there we go. So eventually you should be able to see the drawings that I'm making. Um, so if we go back to he wants a non-inverting cheese and juice. Non-inverting zero crossing detector. So we go back over here. B plus is pin 7, B minus is pin 4. So we'll connect this to uh, 10 volts to make it easy. 1 volt peak to peak is a gain of 10. Minus 10 volts. Pin 6, no, pin 5. Pin 5 is offset null. What does offset null mean? Let me check the lab that I did. Okay, so going off of what we learned in lab, sorry, it took me a second to read it over. Um, Going over what we learned in lab, you can actually you could create a zero crossing with open loop gain. So this can actually be both tied to the same resistor, and that goes nowhere, and then this just goes to the output. So, geez. Since it's trying to force like literally infinite gain, it can't do that. That's not allowed. That's illegal in the world of electricity. You can't get free energy because energy cannot be created or destroyed. Unless, of course, you're God. But hey, look, I might be the God of war, but I know my place. I know my place. Right here in this seat. I ain't going nowhere else. I can't create energy, can't destroy energy. I leave that to that guy up there. I might be the God of war, but he's the God of the gods. Okay, so this right here should detect zero crossing. Mm-hmm. Yeah. Oh, the only thing that's different that I didn't do right, I don't have to put a resistor there to short that to ground. Let's catch up. I don't know why it's not letting y'all see this, but that's it. If you can see that right there, that's what it should look like. I don't know if it's gonna pop up or not, but I'm trying, y'all. So the next one is complete the schematic for inverting crossing one. So for an inverter, this thing is definitely not on track. Like this is definitely not caught up to what it's not up to speed at all. Yeah, see, here's all the see there we go. There we go. That's what I like to see. Yeah, cheese ball. There we go. I like that. I like when stuff shows up. Anyway, so now next part. Draw the same thing, except this one is inverting. So, Chris the Ninja, how do I draw it inverting? What did I just teach you just a minute ago? No, I'm checking for comments because like last time I was not checking for comments at all, and some people were like asking me questions, and I was getting back to them like 15 minutes later. Was not it. Hmm. So for this one, you got to draw this being inverting. Important, the important information right here. Inverting lets you know where it's going. So you want to put this into the inverting input. This gets grounded. This gets grounded. Technically, I need a resistor there, some resistor, doesn't really matter because it's open. It's open the game. We're going to put minus 10 volts. We're going to put plus 10 volts. Output goes here. This is a potentiometer. But yeah, that's how this was drawn. Complete schematic for a non-inverting positive level detector. So if you want a positive level detector, you want to know when the signal has gone positive. We want to know when it's like when it's above basically when it's above zero. So if we want to know when it's above zero, what we could do, I think, now, granted, let me just throw this out there. If you go to my school and you're cheating off of me, you're goofy for two reasons. One, an Aggie does not lie, cheat, or steal, or tolerate those who do. But two, I don't even know if I'm doing this stuff right at the time. So if you're cheating off me and I get the wrong answer and you get the wrong answer the same way I got the wrong answer, then I fix myself. I'm not coming back to the live stream to correct myself. Unless, of course, it's like something like actually study worthy. Like if I'm studying for an exam and I say something wrong that should help you on an exam. But like, I'm not coming back to fix the homework. Once I turn this stuff in, it's turned in. I'm done. Goofy. Don't ask me if I got the right answer. This is what I think I'm doing right. All right. All right. Cool. Polish off dang fruit snacks. You haven't got my blood pressure raising. No, I'm chilling. I'm chilling. I know there's one more. There we go. Yeah, there we go. Mm. Also, these ones right here, goaded. The orange one, goaded. Goaded. Okay. So, I feel like some of this stuff got jumbled up when I converted this into a Word document. Um, But judging off of what where the freak did all the what? Where did all the I was about to say where did all the letters go? Okay, I think. Well, non-inverting. First of all, it's non-inverting. So one thing I can do that's not ever going to get me in trouble when it says non-inverting, connect it to the non-inverting terminal, and this gets grounded. I should always make sure I put some resistor here. This is grounded. I think this 500, let me, well, that's not cheating gonna work. I think that 500 goes over here to this right here. So we're gonna say, um, so we're gonna go back to the schematic. Offset null. Okay, so 1 and 5. I think I can put this voltage regulator to here. Let me look this up real quick because I want to make sure I'm reading the schematic properly, and I'm not sure if I am. Let's see. Oh, okay, okay. Control voltage source. See, I'm glad I looked this stuff up because I was about to draw this completely incorrectly, and I was going to look goofy. I almost looked goofy. Not today. No, sir. Okay, so this is going to be just like 10 volts, positive, negative. Now I want to take a look at the notes that my professor posted and see if there was anything about this stuff. Let's see. Multi-channel. Yeah, so I do that right. Do that right. Okay, so golly, freaking trash all up in my throat, man. Pause. Pause on that. Do I know Boolean algebra? Oh boy. Oh, oh boy. Don't even let me get started on Boolean algebra. Don't even let me get started. You know what? After I finish this homework page, we hopping into some Boolean algebra because I have a feeling I'm gonna have some Gatorade left over. But it's good to see you, my man. Uh Jinjil, good to see you, my man. Welcome to the stream. Thank you for tuning in. If you're still here, of course, there's a chance that you may have left because I wasn't responding. Sorry about that. All right. Anyway, so after looking at my notes to guarantee to ensure I was doing things correctly, um, yeah, that should go there. So this gets that. These both don't need anything. So we'll just put this to a potentiometer, and then we'll put like a 2 volt, a 1 volt battery here. Now it's important to note that you have to still put a positive or negative voltage on the rails because it will have to force it to a positive or a negative. It has to rail somewhere. So when it rails to the negative side, that tells you it's no longer positive, and that's how it can read that. For inverting, there we go. There's my voice. There's my voice, my beautiful, clean voice that has no rattle in it at all. Man, I sound like $1,000,000 right now. I probably don't, but that's okay. That's quite all right. All right. Okay. All right. All right. Anyway, so now that we're on question 4, complete the schematic for an inverting positive level detector. We know what the non-inverting positive level detector looks like. So we're going to have to connect this to the negative terminal. We connect these once again to um, our rails, our VCC and negative VCC. So we'll just call that we'll call this 5 volts this time. And then we put the battery, instead of it being on the negative terminal, as you can see here, you see the battery is going to the negative terminal. So in this instance, we're going to make the battery go to the positive terminal. So we're going to do 1, 2, 3, 4. And this is some reference voltage. So I'm just make a note here. 1 volt equals V ref. 1 V equals V ref. And then put through some load resistor. Some load resistor. That load resistor then, gives you V out. Put this through some load resistor, V out. That goes for all of these circuits, so far at least. And now, next question. Complete the schematic for freaking drop my dang calculator. Scared me half to death there. Uh anyway, um negative level detector. Now, I'm gonna go double check the notes to make sure I'm doing this correctly. But I think hey, your boy just big braining out here. Your boy is just too smart on the sticks. Your boy is too smart on this. Now, here's the problem that I hid right here that I almost let slide. You got to make sure your positive terminal is the positive side is what's going into your terminals. If you have the negative side going to the terminal, it'll flip the output. So for an inverting, you want to make sure you have it there. An inverting negative level detector, you're going to want to put your battery. So we have our battery. You see the negative terminal, positive terminal. We'll say this is 1 volt once again. You connect this here. Assume the wire has enough resistance in it not to short circuit the device. That's what we're just going to assume. Excuse me. And then, of course, as always, we got to connect our rails. Positive or negative, plus 7 volts. Or we'll just say 7 volts because it's plus and minus. Yo, what's good, Crimson? Welcome to the stream. We're just going over this this homework. This is actually my homework now. It's no longer just studying, but I figured I would, you know. Anyway, what the cheese? Okay, there we go. Anyway, once again, we got to connect this to our resistor. That's our load resistor. So R1 is also RL. And then you have V out here. This gets connected to this because you see the negative side is what's reading what the negative voltages are. This connects here. This connects here. And then these are just left, like, you can leave them alone. You don't have to connect them to anything. Like, they're literally being left alone. So don't bother them. Do not, if it ain't broke, don't fix it. Question 6. Design the schematic for a non-inverting negative level detector. That's an important, I know you all should know how to read. Y'all spelled my name correctly, so you got to know how to read. Unless your mom typed in my channel for you and put this on as like an educational video, and then yeah. But I assume you know how to read. So this isn't made to like to insult anyone's intelligence or anything like that, but it's important as an engineering student, as an engineer, as a doctor, lawyer, businessman, accountant, whatever you do with your entire life, it's important to read the instructions carefully every single time. I don't care if you think you know what you're doing. I don't care, because you're going to read something one day and you're going to overlook one word that will change the entire outcome of what you're supposed to be doing. If it says use screw A, not screw B, and you use screw A and screw B because you just flew by it, like screw A, screw B, okay, cool, use both of them. Now you're missing the screw somewhere, and your whole microwave falls apart. When in all actuality, if you had just read for 1 extra second the word that says non-inverting, you read for an extra split second non-inverting, it'll save you so much time in your life. Life lessons with study sessions, hosted by Chris the Ninja. Anyway, once again, we're going to connect. Actually, I'm going to use a different color for this time. I like blue. So we're going to connect our voltage. We want it to be non-inverting. See, I did an inverting one before. My professor, I know, Dr. Hudson, I'm on to you. I know what you're doing. I know what you're doing. You had it set up where we would think that everything was just going to be inverting, non-inverting, inverting, non-inverting, inverting, not. You switched it up on us, and I see you. I see you. I respect you for that. Well done. Well done, sir. So then we got that. Connect the voltage levels. This is just like make it clear, because I know it can get a little jumbled. And then we need to make a battery. So we have minus positive. It's positive, plus, minus, gosh, cheese crackers connected right there. Okay, so now eventually you should be able to see this pop up. And then this gives you the amount. So this is the schematic uh, for a non-inverting. You could tell that's non-inverting. You could tell it's non-inverting because you could see that the input voltage that we're going to be measuring, the signal, is going to the positive terminal whenever it pops up. And you can see that the negative terminal has its battery connected. There will be some voltage here, so like we'll just say like 2 volts, doesn't really matter. But because and it doesn't, I don't have to notate that the battery itself is negative voltage. The fact that the battery's backwards shows you it's negative voltage. When the positive, it doesn't like the voltage is going to be the same. In all actuality, there's no such thing as positive or negative voltage. This is like a personal opinion. In all actuality, there's no such thing as positive negative voltage. The difference is potential difference is either leaving or entering the circuit. If the potential difference, which is what voltage is literally defined as, potential difference is entering the circuit, it is a positive for the circuit. But for the battery or capacitor, whatever it is, it's negative to that component. If you were to flip it and you're putting voltage into a battery or in a capacitor or whatever, now leaving the circuit, it's a negative voltage, but it's a positive for the battery. So there's no such thing. It's just a matter of perspective. It's all relative. Um, Schematic. So an adjustable voltage regulator with a plus or minus 12 volts, with plus or minus 12 volts of power and a range of -4 to +4. Hmm. So that means we need to have some type of gain in this circuit. Um, we need some gain. Got to get them gains. Our circuit has to go and hit the gym. So if we have if we're powering the circuit with VCC, so we power the circuit here with 12 volts, and then we power it here with -12 volts. That takes care. That takes care of this plus minus 12. Now we want it to be a regulator. We need the gain to be 4. So we're going to have to connect this, this, and then this will have cheese crackers. Cheese and crackers, man. This is ugly, but it's fine. Let's say 1K, and this will be 4K. That'll give us a gain of 4. 1 volt peak to peak. We wanted a gain of 4. Bam, wham, bam. Thank you, ma'am. Let me check the notes because the notes are telling me everything I need to know. Okay, so going off the notes that I'm given, you have your input. Your your input voltage, your whatever the signal is, go, goes into the positive terminal. So that gets grounded. Then Yeah, that doesn't have any coming back into it. Um, then instead of that, you have goodness gracious, I'm about to drop my iPad. Jeez. Trust me, I'm a responsible student. I'm responsible. You have I'm gonna draw this way out here so it can actually be seen. Wait, no, 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 no. In my heart. Mella made it right. I got pain in my heart. I told you 100 times. 10 kilo ohms, 10 kilo ohms. And then this right here, you want to have this be a potentiometer. Wait, no. Gosh, geez, bro. I'm drawing this all kinds of messed up. But hey, this is how you learn. This is literally how people learn. Restart this. Restart this whole stupid. Jeez. Okay, so we take this. This is a 10K. We take this. This is also a 10K. Now we take this input here, and that connects to a potentiometer. There we go. I don't know why it looks so messed up. Like this just looks weird as heck. I'm gonna turn in what I have on my iPad, not whatever this monstrosity is. I couldn't tell you what the cheese is going on over here. I couldn't tell you if like like cheese, what is going on here? Um, what time is it? Like 6:36? Dang, okay. How many more we got? OPAs. Oh, next question. Please pop up. I'm missing question 7 and 8. Complete the schematic for an inverting amplifier with a gain of 50. Okay, so I don't know why this isn't like coming up, but we're just gonna go ahead and okay, there we go. Now it's back. Um, complete the schematic for an inverting amplifier with a gain of 50. Now, what did I just teach y'all? What did I just teach y'all at the beginning of the stream? Rewind the stream, go back, and tell me what I just taught y'all. I'll wait. Welcome back. Now, see, y'all might be like, oh, Chris, there was not enough time. This is a YouTube video. This is a YouTube live stream. You can pause the stream. You can come back to it later. Like, I'm just going over electronics and stuff. Like, it's literally not that deep. Jeez, relax. Oh man. Y'all crazy, man. Okay, but for real, boy, draw an inverting amplifier with a gain of 50. So, inverting amplifier. That's the first piece of information we have. We have a gain of 50. Now, what I taught you all in the beginning was that the gain of an inverting amplifier is this equation. So minus RF over RI. Now, there is no such thing as a negative resistance. That's called allowing something to go through. Like, what? Do you have negative blocking stats? Sometimes I think the Bengals offensive line has negative blocking stats. Sometimes I think the Cowboys against the Packers has a negative offense stat. uh, shout out to the Cowboys and the Bengals. I love y'all. Love y'all. Joe, get just go to Cincinnati High School. Grab any of the offensive linemen off their high school team. You will have better protection immediately. I'm just saying. Look, I'm just saying. Anyway, so we're gonna take our input. We're gonna ground the input, and we'll have doesn't really matter. We'll just say like 1 volt or 1 millivolt peak to peak, and then that connects to the inverting side of the that connects to the inverting terminal. Now, is anybody in the chat? If anyone's in the chat, it doesn't look like there's anybody in the chat. It's just me. It's me because I'm just looking over like to make sure no one has questions. But let's just say what uh we're gonna use our favorite. We're gonna use my favorite number. Actually, no, 50. Fun fact about the number 50. 50 was my first football number. I was before I was 76. I was number 50. I was the coldest defensive tackle on the team. My man Guy, his name was actually Guy. My man Guy, my boy Micah, crazy defensive end. Then Sneed, James Sneed. That dude hated me, bro. That man hated me. But that man was cold, bro. He was so cold. That dude was a great football player. He just hated me. uh, so we'll put 1 kilo ohm here. Now this is the point where you have a feedback. So this is like your V out here, but you need to have a feedback, and that's what creates that closed loop gain I was telling y'all about. And to get a gain of 50, we would need to put 50 kilo ohms here. And in general, you shouldn't exceed like 100. I think you shouldn't exceed 1 mega ohm for your like for your highest resistor. So like you could literally put like a 1 ohm resistor and a 50 ohm resistor, but you know that will probably burn up. You could put 100 ohm and a 100 ohm and a 5,000 ohm. That would work, right? No, wait, yeah, 100 ohm and 5,000 ohm. That would work. Um, there's a infinite number of combinations you could make to get to a gain of 50. Positive terminal that gets grounded, and now you have yourself an inverting amplifier with a gain of 50. And then what is the input resistance of the circuit of my circuit based on the values chosen? Input resistance or RI, equals 1 kilo ohm. This right here is negative 50 over 1, or 50K over 1K. That simplifies to 50 over 1. And that gives you a gain of, well, technically a gain of minus 50. That's the reasoning behind it. Um, Next one, complete a schematic for an inverting amplifier with a gain of 500. Now it's the same concept, the same exact concept, except we're scaling up a lot more. This is V out. Also, this stuff ain't due till the 6th. So I'm call me an example because I'm setting examples for all of these kids out here, man. Get your homework done early, play some Madden after you finish your homework, drink a Gatorade once in a while, go outside and get some oxygen. Like I'm just I'm just that guy. Yeah, I'm just that guy. I'm just so wholesome. Um, so now we're doing the same thing. We're doing another inverting amplifier. That's a very important concept, a very important thing to notate. Inverting amplifier. We want a gain of 500. We want that gain to be 500. We want that big gain. So today we're going to pull out our handy dandy calculator. Let's get it, dog. Let's get it. We do. Oh, oh, we do 76 times 500. Okay, 38,000. So we'll have, and what the cheese is this? Is this hair? Oh, I thought that was a crack on my screen. I was about to murder somebody. All jokes, of course. That was a joke. FBI, if y'all are watching, that was a joke. Relax. I got too much to lose to throw my life away like that. That's crazy people stuff. So we have our uh our voltage here. Got that with 76. Ground that. This gets grounded as well. Um, these these rails here, uh, the rails here, right here, these literally don't matter at all. For an inverting amplifier, it doesn't matter right now. And then we have our feedback. $38K resistor. So you got a 38K resistor. So now input resistance Ri equals 76 ohms. And that's it. It's that simple. Literally that simple. Complete the 5-channel inverting adder amplifier with a gain of 1. So an adding amplifier or summing amplifier, uh, I got to look back and remember how to do this. Okay, so to make a summing amplifier, to make a summing amplifier, or an adder amplifier, I think they're the same thing. Yeah. So an inverting adder, um, he wants 5 channels. So that comes out to here. Just gonna draw that line out a little further, and then we're gonna break R1, R2, no D2. Don't unsubscribe. R3, R4, and R5. I think those are all connected to. And those are each connected to their own voltage source. So we'll put V1, V2, V3, V4, 5. Doesn't really matter what the voltages are. Not not really in the slightest does it matter. Um, oh, inverting. Oops. Teehee. So that connects there. There we go. Um, this takes this. This feedback comes around here. This RF value right here. Yeah, so got that RF value. This gets grounded. And then you have your load resistor, and that gives you the out. The way this works is that you have, if you wanted to have a gain of 1, you just say assume RF equals R1 plus R2 plus R3 plus R4 plus R5. So if we have RF equals 76, then let's just say R1 equals 6, R2 equals 10, R3 equals 15. That's 25, 31. This equals 5. So that's 36, and this equals 40 ohms. That's a that's a way to one way to do it. So now the next 3 questions are look it up questions. Um, so this is how we as engineers learn how to use data sheets um, to find information that we want and information that we need. I'll take big breather, big breather. Oh, yeah. Okay. After that quick brain break, because you always need a little brain break. Can't ever be anything too weird, too crazy. Can't be anything too crazy because if you get too crazy, you start going crazy, you know. So now what we're gonna do is we're gonna look up the LM 356. Wait, is that LF or LF? No, LM 356 op amp. Um, maybe it was the LF 356. I don't see an LM 356. I might need to email my professor about that. Where's my mouth? There it is. That's 358. Yeah, that's an LM 356. I'm not crazy. Boy, I'm not making an account just to read this stupid thing. Man, I'm not putting I don't want to do this anymore. I don't want to do this anymore. They got me messed all the way up. I don't want to do this anymore. This is rank. This is rank. Freaking cheese cracker had to freaking watch a dang ad to relax, breathe, 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 breathe. Oxygen, oxygen. Ah, y'all. I'm about to play. I'm about to go God of War on this entire website. Okay. What is it ask? What is he asking for so I can know what I'm looking for? Input resistance, input bias current, and offset output offset voltage. This isn't even the right freaking thing. This is an LF. I honestly think my professor may have had a typo. So I'm emailing. I'm emailing because he's cool like that. But I enjoy having professors that are great that you can just email and ask questions. Homework one. Working on homework one now. I am trying to find the LM356 op amp. However, the only one showing up is an LF56. My question is, was the M a typo? Best wishes, Chris Carter. Okay, cool. So I just sent him an email. Worst case scenario, yeah, it looks like the only thing is the LF356. So I'm just gonna have to pull this. All right, but anyway, okay. What do you want to know? He wanted to know input resistance. It depends on input. So if you look to the right of the screen, you can see the units. So I'm looking for ohms. If I can find ohms, then I know. Let's see, gain bandwidth. Oh, see, look. This is what I told y'all. At certain gains, this is what I was telling y'all with the graph I drew poorly. has a certain gain at different bandwidths, different frequencies. Output impedance. 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 Control F. High input impedance 10. Wait, 1 giga tetraohm? It's into the 12th of tetra? It is 10 to 10. 1 trillion is what is the tetra prefix? Um, engineering. Tera, not tetra, tera. A teraohm. Jeez, man, my goofy, stupid, looking freaking idiot. A teraohm. You can see it here. 10 to the 12th ohms, that's 1 teraohm. Goofy. I don't know why I thought it was a tetrabyte like it's terabyte. Goofy. Need some brain damage to fix my freaking mind. Input bias current, 30 picoamps. 30 picoamps. What is the output offset voltage? Storage output. The offset voltage. Hold up. It said offset voltage, right? The output offset voltage. Voltage swing input bias current. Supply voltage. Um, high voltage. High voltage, output voltage swing. I'm trying to find it. Output offset voltage. Input capacitance, slew rate. Offset voltage. Offset. Um, offset voltage. Low offset voltage. Okay, I'm gonna look up the LF356 output offset. What is the output offset voltage? VOO. Let me see. 'Cause I gotta like go digging for this. I'm sorry that I'm not really saying anything. So you have to go dig for this information. Oh, let's see. Power dissipation is not it. Output impedance. That's not what I'm looking for. It's not what I'm looking for. Booty plot, common mode rejection, power supply rejection, frequency, detailed description, feature description. Okay. Asking for what? Voltage, output, offset voltage, output, offset. There's nothing in the data sheet about it. There's literally nothing in the data sheet about it. Um, there's offset voltage, but there's not. Let's see. Oh, okay, okay. So I can find that with an equation. So output offset voltage. So given the input, shut up, you freaking ad. Nobody wants you. Input offset voltage. So we'll say 10 millivolts. 10 millivolts. Input resistance, feedback resistance. Let me see. So we have 10 millivolts. So that's 0.01 multiplied by input and then feedback. So I need feedback resistance. Um, feedback. It looks like I have to use 2 kilo ohms for this too. So we have 2000 plus 10 to the 12. And that's 10 to the 12 divided by this. That's 1. So it seems like it's 10 millivolts. We're going to go with 10 millivolts because equation, the equation came out to be like basically that. So 10 to the 12 divided by 10 to the 12 plus 2000 equals 1. V equals 10 millivolts. Man, that one took a minute. That one took a minute because I couldn't find this. Couldn't find this stuff, man. Like absolutely insane. I couldn't find it. Um, I have video evidence that I looked for like 15 minutes, but geez, bro, can't find. I mean, if you can't find stuff, you can't find stuff. You know, it is what it is. It just is what it is. Um, complete the schematic for a 7-channel inverting averaging amplifier. So we're back to drawing schematics again. When is my time? I'll know. Never seen a wind come. Okay, so to make an averaging amplifier, um, he doesn't specify what the gain needs to be. Yeah, he doesn't specify any gain, so we're good to do whatever the cheese we want. When is my time? I don't know. Freak it, screw it. We're doing it the regular way. So he wants 7 channels. He wants it to be inverting. Once again, I say to you, inverting, you got to put it on the inverting channel. You got to put it on the inverting terminal. All right, yeah. Put that on the inverting channel. This is text wrapped, isn't it? That's why this is. Ugh, calm down. Relax. It's all good. It's all good. It's fine. Fine. It's not really fine. Everything's okay, but it's not really okay. My life's a death race. Okay, so we're going to make this nice and easy. So we have V1, R1, V2, R2, V3, R3, V4, R4, V5, R5, V6, R6, and then V7, jeez, V7, R7. V7, R7. All right, cool. Now, RF, our beautiful, beautiful RF, just has to equal RF just has to equal R1 to R7, R1 plus guessing R total over the number of resistors. So we'll just say 5, 5, 5, 10, 10, 25, 10, 35, 10, 40. So 30, 45, and then 31. Wait, yeah, 31. So then we just pull out our handy dandy calculator. Do 76 divided by 7. And we get 10.85 ohms. So we'll just round that up to 11 ohms. Then the rest of it is basically the same. This gets grounded, and that should do it for that. Yeah. OPA 1663. And then the last two are just lookup problems. Um, so I'm gonna just go ahead and look those up on my own. Um, I hope y'all don't, if y'all have any questions, I mean, you can drop them in the chat right now. Leave a comment if you have other questions. I'll try to answer as best I can. Maybe I'll do another study stream where I just do Boolean algebra, because I've been doing homework for like an hour 15 minutes. My brain's tired doing all these circuits and stuff. But I mean, as long as y'all like it, as long as y'all having a good time. But with that being said, I want to say thank you guys so much for watching this study session. If you liked it, get the like button, get the like button a nice slap in the face. Like and our see all you guys. Oh wait, subscribe today to join the Shinobi. Um, comment down below what subjects I should also do. Maybe I'll pick your subject next, or maybe I'll cower away from it because I don't understand anything about it. But yeah, and I'll see all you guys. Well, one to do with fast stars on the wall next time. All right. Hold on, let me stop sharing. Oh freak, shoot. Stop share. All right, yeah. All right. I'll see y'all around.